So without further delay, here's your Delphi instructor.
Hi, I'm Dave Hobbs for Delphi, and welcome to this program on Diagnosing to Win with Fuel Trim. Maintaining the mixture. Now, why are we getting into a program on fuel trim? Because it has to do with not only rich codes, but lean codes, and lean codes are in the top 10. Actually, they come in at number 3, the 171s and 174s, generic for lean left bank, lean right bank, or lean bank 1, bank 2, and plus all the other manufacturer-specific P1 and other number codes that for various things that have to do with air-fuel mixture. So let's get started and talk about what we're going to be covering in this very action-packed, with demonstration, live cast brought to you by AVI. Short-term, long-term fuel trim terms are really defined along with total fuel trim, and we'll throw rear fuel trim in there as well. Graphing your fuel trim numbers on your scan tool to get the most out of your diagnostics. Looking at misfires and false air, exhaust leaks, vacuum leaks, and fuel trim numbers, what to expect and so forth. Might be some things, even if you are a pretty high-end drivability tech, you might pick up a few extra things, and if you're in the middle of the road, like most of us on this topic, you're gonna get a lot of stuff out of this program. We're gonna talk about long-term adaptive memory, clearing memories, what those memories, how they work, and so forth. So let's get started here and get into short-term fuel trim. What is it? It is the knee-jerk reaction of the computer seeing the O2 sensor change. And as it sees a trend towards rich or lean, it's going to make corrections almost immediately when we see low or high O2 voltages. We'll talk a little bit about the wideband, but mostly switching switching O2 sensors. It should be around 0% ideally, but we know engines don't run ideally. We're going to see fluctuations within the 10% of adding fuel, positive, or percentage negative, taking fuel away if it's being sensed rich. Could go as high as 25 to 35, either negative or positive, rich or lean. But when we see those kind of numbers, almost assuredly you'll get the mill on for a rich or lean problem. It's an indication of the trend, what's going on with the engine. And it's an old term, OBD1 days. If you're an older tech like me, you remember integrator. That was the same as fuel trim, with 128 being the magic number for General Motors, and also for VW and Audi, they call it multiplicative mixture correction. So we move on to long-term fuel trim. Basically, it is going to be following short-term. So it is a percentage of injector on time, as is short-term, and the range is the same, positive or negative 10%, within a window of acceptability, but if we see 20 into the 30s, we're going to set the mill. Long-term fuel trim is an indication of engine conditions overall over the course of different driving conditions. And those driving conditions are stored into what's called memory cells, and that is in non-volatile NVRAM. That's random access memory. In other words, you turn the key off, most vehicles you're going to maintain those numbers that either were updated 2 minutes ago or 2 days ago. When we got into that parameter of either the mass airflow blocks, how many grams per second, under these conditions, we set a fuel trim update. So we looked at the short term for a period of time and then went to a longer learned fuel variation called long-term fuel trim, plug that in, and when you clear that from memory or do a battery reset, you will have new numbers. So more on that coming up. Long-term fuel trim cells are stored under different operating conditions. As I mentioned, it could be mass airflow parameters, or it could be an XY graph we'll look at later, where we look at load versus RPMs. Now, another term be called total fuel trim. Now, total fuel trim is adding short-term and long-term together. For example, if for whatever reason our long-term would go 22% positive, so we've learned it over a long period of time, we needed to add 22%, but at a precise moment, we see -8 on short-term, we'll add those two integers together. So -8 and positive 22 equals positive 14. And here's a tech tip for you already. Rear fuel trim is the O2 sensor, and they're always a switching design, the 0 to 1 volt sensor behind the catalytic converter. So the rear or post cat O2. Rear fuel trim is taking in consideration a little bit of variation of how the engine management air fuel can be driven by the rear O2 sensor. Now, in most conditions on vehicles that do use this value, it is very minimal. Under certain conditions, like degraded front O2 sensors, rear fuel trim can be very profound. So therefore, if you see a P.I.D for total fuel trim, but you don't see one for rear fuel trim, you see short term, you see long term, and you see total fuel trim. And the total fuel trim does not add up to the short and the long added together. It's a number higher or lower. It's because long-term fuel trim, the after the catalytic converter O2 sensor, is driving that total number for whatever reason. So that's how you can see it if you don't see a P.I.D for rear fuel trim, as many aftermarket or even OE level, but not true factory scan tools, do not show rear fuel trim as a P.I.D. Something to keep in mind when you're doing diagnostics. Look at that total fuel trim, because total fuel trim is what a tech needs to go by in diagnostics, because it's what the PCM goes by in diagnosing whether we have a rich or lean condition worthy of turning the light on. Now, because they work together, short term is a knee-jerk reaction directly basically moved by the O2 sensor. Long term follows the short term, so the O2 sensor drives short term, and the short term value drives long term value. And after a certain period of time, the long term updates and the short term then may come back to zero, or they may both move in a particular direction depending on what the O2 sensor value is reading. So that's how that works together. And just to keep the relationship in mind, because a lot of techs that don't pass ASE A8 engine performance, and especially those that don't pass L1 advanced engine performance for ASE testing, one of the big things they trip up on is the relationship between O2 voltage and fuel trim, and whether we're adding fuel injector base pulse width, we're adding to the base pulse width a little more injector on time, or subtracting some base pulse width on time. What is base pulse width? You flip the key on and you see it. What is the mass airflow, the MAP, the coolant, intake air, all those analog and digital sensors the computer looks at, and then you start cranking RPMs and so forth, and it makes the decision to spray the fuel injector X amount of milliseconds. And after the fact, if that's too much or too little due to engine problems or variations, mechanical variations, variations in fuel, for example, we'll be talking, we do a little live demonstration on alcohol and fuel. As that is not perfect, then the O2 sensor sees that, we make adjustments. So you see, as we move from the center to the right, we're adding fuel with a positive trim number, and that's because of a lean exhaust. That would be in a switching O2 sensor value, a number below 300 or 400 millivolts, somewhere low. If we go to the left, we're taking fuel away, a negative percentage added to the base pulse width, taking some of the spray on time away, less on time with the injector, to respond to a rich condition, O2 measuring a higher voltage, 600, 800 millivolts or higher, and we're going to lean it out. So that's how those work. That relationship is pretty basic, but it can sometimes be a little tricky, and we kind of get things backwards. We talk about misfire from ignition events, a bad spark plug, a bad coil, and how that affects fuel trim. A lot of techs get a little mixed up there, so we're going to make sure we cover that thoroughly in this program. Now here's a question for you right off the bat here. Tech A, speaking of ASE style questions, Tech A says a negative short-term fuel trim and a negative long-term fuel trim indicate a rich mixture. Tech B says they indicate not enough fuel. Who is correct? Make your choices on your computer now. Should be an easy one for you.
%of our respondents picked technician A. 12% picked technician B, and 0% for answers C and D. So they went with A.
They went with A. They were right. This is a very good, easy, fundamental question. Most of you got it right. That is great. When the fuel trim numbers go negative, as we saw on that chart just a second ago, that's because it's rich. We're taking some fuel away. We're reducing the amount of injector on time by a particular percentage, especially if both short-term and long-term go in the same direction. All right. Also important to remember, as I said, O2 voltages drive short-term, and short-term drives long-term, and rear fuel trim does make subtle adjustments. Most manufacturers will say it's a very small number, anywhere from a fraction of 1% to 2 or 3 or 4%, typically single digits. However, under certain conditions, like I said, with maybe front O2 sensor degradation, we can have more authority by the rear O2 sensor. So keep it in mind as you think total fuel trim when you diagnose air fuel management issues. Now, also in diagnosing air fuel management issues, always look at not only your O2 values on a graph, so put your scan tool in graphing mode, but also look at your trims, both of them in graphing mode. Now, here's a case where I asked you a question: what could have caused this? As we look at short term, first of all, in the lower picture, as we follow from left to right, lower graph, we're seeing about a 0 to 6% positive fuel trim number on short term adapt. And then it takes a dive, so it's fluctuating back and forth. Now, if you were just watching your scanner in the digital normal format of data display, you would see the number popping around. You might catch it and it says 0, you might catch it and it says 6. You want to see what it's doing overall, kind of what the computer's doing. So we're seeing it is adjusting quite rapidly. You would actually be able to lay the O2, pre-CAT O2 sensor graph on top of short term, and they will be just the opposite of each other. So as O2 starts going down, being leaner, you would see shortly after that, like almost immediately, but not exactly immediately, you'll see the trim go up, and as the O2 value goes back up, as it shifts back and forth to keep the catalytic converter happy with oxygen storage, and also make sure the computer knows that the O2 is working because it's switching back and forth. We will deliberately do that with fuel injector pulse width, slightly varying each side of stoic. We'll also see the trim move back and forth too. So that wiggly trim you see in the bottom picture, that's normal. And you see about an 8% additional for long term as well. So it's watched the short term for a while and compensated and moved up. Look what happens when the short term takes a dive down, meaning it's taking fuel away. It goes down to about -17. And the long term follows after that. What could have caused that? Well, it could be an issue with a drippy injector, because we're spraying too much fuel, or dripping the fuel, I should say, and it's making it rich. O2 goes high, trim goes low. But it could be something that's normal, like onboard diagnostics, OBD2, running not an evap leak test, but an evap canister saturation test to see if the canister indeed did store vapors, and we pull the vapors in, turn the purge on, leave the vent open, pull some vapors out of the canister, and as we use them in the engine and don't compensate, assume we had something to burn, we just let the base pulse width remain the same, and we pull those vapors in addition to the fuel spray of the injector, we have evap vapors. We're going to have a richer mixture. The trim goes down. When the PCM sees that, it says, hey, the evap's working fine. So fuel trim and O2 sensors really integrate into a lot of other things as well, including normal OBD2 intrusive tests like that. So that's a normal thing you might see, but you're really looking to see the trends in both short and long term. Now, to keep the relationship straight for everybody so we can all pass an ASE A8 or L1 sometime in the future, very important for that, you look at what the overall numbers are, and you keep this little graph in the back of your head. In green, we're 0 to 10, positive or negative. We're cool. No big issues there. Normal engine variations can cause a fluctuation between 0 and 10. You might see a little into the teens, you start raising an eyebrow. You know the PCM is, that's when mode 6, we see things getting a little bit close to the edge and flagging a yellow number in the TID, SID, so forth categories. When we look at a mode 6 on a PC-based scanner, they can give you multi-colors. And so we really don't typically see a light come on. It's going to vary from manufacturer to manufacturer, engine to engine, until we're in the red, positive 20 or negative 20. So green zone, good. Yellow zone, maybe a concern. Red zone, if the light's not on, it will be. Fix the car before it leaves. You see the 128 number, by the way, a little trivia. That was the old block learn integrator numbers from General Motors. 128 was stoic, no trim adjustment, and a number below 128, 100, or above 128, 140, that was adding or reducing fuel. Now, as we correlate this into what the O2 sensor activity is doing, upper left-hand corner, we've got a good switching time. We don't really have an x-axis to tell us what the time base is, but we'll just say it's switching at 80 millisecond, which would be a decent switching time for a O2 sensor, a switching design, conventional O2 sensor, and it is going as high as, say, 900 millivolts, and as low as 100 to 150 millivolts. That's a good O2 sensor. But if we see over in the lower left-hand corner an O2 sensor is biased lower, it doesn't really get much over the 450 millivolts of bias voltage provided by some PCMs to to the sensor. It mainly hangs out below that. So that's indicating we're running lean. So we have a lower air-fuel, have a higher air-fuel ratio, actually a lean ratio above 14.7 to 1. You look at the upper right-hand corner and you see it hanging out high. We don't get much below 450 very often, 450 millivolts, but we do see 900 millivolts a lot. So that's a rich mixture being sensed. That's going to result in a lower than stoic number, we'll say 12 to 1 air-fuel ratio, and that's going to result in a fuel trim number that needs to go lower. And the picture on the lower right-hand corner, that's a O2 sensor that should set a code, but if it doesn't, don't pay attention to your fuel trim, because whenever you have an O2 sensor malfunctioning, don't pass go, collect $200. Fix that problem first. Misfire is the same way. Fuel trim can be worked on later if you still have a problem. So make sure you got a good O2 sensor to work with. Now, as we move all this together, the graph that showed fuel trim acceptability, borderline in yellow, and then red should set a code and how it corresponds to the actual O2 values. If we graph or scope an O2 sensor of the traditional switching design, as we see it go full rich and full lean, not hanging out either one of those two places, a good switching time, we see it in the green, 0 to 10 either way. But as we see the upper right-hand corner hanging out biased high, that's a rich mixture, high O2 voltage, rich mixture. We're going to go negative into the red, and that's going to be reducing the base pulse width by a particular percentage. The same thing, lower left-hand corner, that O2 pattern is biased high. We're really rich, or at least the computer is seeing this because this thinks it's rich, and we start to then have a positive number, lean. It's lower, bias low, it's lean, so it's going to add a positive number. Too much air, not enough fuel, we spray more fuel, we increase the base pulse width. Now, question for you to answer back on your computers. Vacuum, this is a little more difficult, by the way. Vacuum leaks on speed density vehicles. That's vehicles without a mass airflow, MAP only, MAP. What effect do they have on fuel trim? They have no effect on fuel trim, A. B, can drive fuel trim slightly higher or lower. C, decrease MAP voltage. Or D, cause fuel trim to go very high. Make your selection now.
Okay, I've got your results, Dave. 20% chose A, 50% chose B, 0 chose C, and 30% chose D. So they went with B.
But okay, great. Well, you who answered B, bravo, are correct. Now, why wouldn't it be D? 30% did select D as in Delphi. Why isn't that the correct answer? We're going to find out as we look at a late model vehicle with a wideband air fuel sensor and speed density system. We're going to do a live demo. That's one of our first demos we're going to do in this program. We're going to see that a big old vacuum leak on that speed density vehicle had very little effect, ironically enough. And as you remember, if you're a tech who worked years ago on throttle body injection, like with GM Chevy V8s, for example, the gasket between the manifold and the throttle body, notorious source of leakage, just a bad gasket. Well, the idle would go up because speed density systems sense less vacuum. Therefore, it adds more fuel to go with it, like there's a greater load. It makes the engine RPMs go up if you don't have throttle by wire. And now you have an excessive idle speed. If you remember, sometimes you saw a little bit of a negative fuel trim because it really didn't have an air fuel management issue. It had an idle speed issue at speed density. On a mass airflow vehicle, a different story entirely. D would be the correct answer on a mass airflow equipped vehicle. If we had a big air leak, you'd see the fuel trim go up and you see the vacuum voltage on the MAP sensor also go up as well. So the correct answer, it can go either way depending on the vehicle, slightly higher, slightly lower, if you have an air leak on speed density vehicles. Now, let's do the on-car demo on that vehicle I was just talking about. Working with a late model Ford non-gas direct injection, so it's got regular sequential fuel injection, no turbocharger, and no mass airflow. So it's speed density looking at the MAP sensor only. Now we have the new wide range air fuel sensors on this vehicle before the catalytic converter and a switching type O2 sensors, conventional voltages you'll see after the catalytic converter. So we're not going to really see the actual 0.1, 0.8, 0.6 volts of O2 like you may be more used to seeing on older vehicles. We're going to see lambda and current for the pre-catalytic converter sensors on both bank 1 and bank 2 of this 3.5 transverse V6. So we got RPMs. I'm going to highlight those. We're idling along here. The O2 sensor before the cat is showing 0 milliamps, so we're not having to compensate too much there to make that sensor read stoic. The heaters we don't really care about at this point, but we do want to look at the sensor after the catalytic converter, just as a comparison, and also look at fuel trim. Those are going to be their biggest ones right here, so we'll look at long-term fuel trim. Alphabetically, it comes up first here, the L for long-term, bank 1 and 2, and of course short-term, bank 1 and 2. And this one actually does some post-catalytic converter O2 sensor fuel trim as well. So we look at these guys. We'll go ahead and look at post O2. Those are the switchers, the 0, 0.1, 0.2, 0.8, 0.7 volt type sensors. So we'll go ahead and hit done. I believe that's about all the PIDs I really want, except maybe let's go ahead and look at lambda. Lambda 1 will be 14.7 to 1 air-fuel ratio. When we go higher than lambda 1, think of it like air-fuel ratio. A ratio that's higher than 14.7, let's say 16 to 1, that's leaner, 16 parts or pounds of air to 1 pound of fuel. If we go richer, you can smell the exhaust, you know it's really running rich, you got black spark plugs. Now we're seeing numbers like 11 to 1, 12 to 1. That's below 14.7, so that'd be a less than 1 for lambda. So greater than 1 means lean, the ratio of air is going up, and below lambda 1 would be rich. We're going below 14.7 with much less air to 1 pound of fuel. So we'll go ahead and select that list right there and say done. So we'll make our PID list even smaller than this customized O2 section that we're looking at of several hundred PIDs total on this late model Ford that we could see. Now that's drilling down to look at your air-fuel issues, and we are well in control. As I highlight long-term as well as short-term fuel trim numbers, they are all in single digits. They're low single digits, positive, negative, doesn't really matter because we're looking at the two together, 2 positive on our long-term and 1 negative on the long-term. That counters out, so our total fuel trim 2 plus negative 1 would be about 1. So that's 1% of any kind of a multiplier to change our air-fuel ratio from what we originally destined the injector to spray to what the O2 sensor reports back in and says, hey, that was too much fuel or too little fuel. I'm smelling a lot of O2 left over or no O2 left over. So very little change, very little correction, and we got an RPM, nice low RPM, 600 RPMs. That O2 sensor that is a wide range sensor is reading before the cat on bank 1. It's reading 0 milliamps. So we're not putting much current in there at all to make the O2 sensor respond to a rich or lean mixture to get that wide range of air fuel. So that's pretty much normal. Now let's just pull a big vacuum leak and see what happens. On a speed density version of this late a model of vehicle, it may not make a big difference. As I've noticed, the newer these cars get, the harder it is to really see much change when we do bugging in the field. So I'm going to take a big vacuum hose loose right here, right off the manifold that tees over here to the vacuum booster. Now I can feel that big leak, big air leak right there. So I've got an air leak. Our numbers should go positive. They both are, both long-term and short-term, but not radically. So even with the big vacuum leak like here, we are still fairly much in control because being a speed density car, we are compensating for that extra air going in the engine as we see the map voltage change by adding more fuel to go with it. But it's still a little bit lean, so we're adding some fuel, 0.2 or 2% on long term, 1% on short term, for a total of about maybe 2 or 3%. Very much in control. The O2 sensors after the catalytic converter hanging in there and being very unresponsive, which is typical after the cat. Now let's go ahead and do a opposite situation. We'll take the propane, not going to light the torch, of course. I'm just going to put some propane in. Now there's a better fixture to do this. If you have that back from the old carburetor days, that's fine, but this will suffice. So I'm going to go ahead and turn on the propane and replace a vacuum leak with a very rich mixture. So there's my propane turned wide open, and you see those numbers go negative on the short term and the long terms will probably follow down later. So we're seeing compensation going on, maintaining 600 RPMs. We're compensating about 6-7%. It went to about 10 at its prime. Negative, so we're taking away fuel because the propane is adding fuel. So the O2 sensor is going, man, there was not a whole lot of O2 left over. We're rich. Computer says, let me lean those injectors out by narrowing the pulse width of the injectors thanks to the propane. So we got a really nice system now going. We've got some, this is delayed. There's actually a data PID you can see on delayed action or reaction with fuel trim, and that's actually a bidirectional PID on some scan tools that you can counter that. You can actually turn that off and see an immediate response when you turn the propane on. I'm getting a good response now. I would say if we continue doing this, driving down the road, we'd probably set a mill for a rich mixture, both banks. Well, that last question we had about the effect on fuel trim of a vacuum leak on a speed density vehicle was kind of answered there on that Ford Explorer, very late model vehicle with the newer air fuel ratio type of sensor. It had a small effect, but not as drastic as one might think. Now, here's another question for you. Speaking of those new style of O2 sensors, sometimes called wide range, sometimes called air fuel sensors, but regardless, they're not a switching sensor, which is either saying rich or lean. It doesn't really tell you how rich or lean it is, but those have been the O2 sensors since the 1980s, and they're still used behind catalytic converters, but most cars have switched, not all, but most cars have switched to a different type of sensor. In the video, you saw a PID value for the pre-cat sensors for oxygen. What did those sensors do? Here's the question. An O2 sensor of the air fuel sensor variety, the PID is fluctuating between a very low positive and a very low negative current value. Very little movements of current, positive and negative. What is most likely going on? A, the sensor is internally shorted to the heating element. B, the sensor is in a diagnostic mode for the heater. C, the PCM's 5-volt reference is bleeding over into the O2. Or D, the sensor is a wide range air fuel sensor that is working to specifications. Make your selection now.
I've got the results, Dave. 0% chose A, 0% chose B, 9% chose C, and a whopping 91% on D.
The 91s, you have it. That is the exact answer I'm looking for. Now, you know that you saw in that hands-on demonstration, and if you've had your scanner on newer cars with the wide range and the air fuel type sensors, they are a much more integral, or I should say complex sensor. Basically how they work is they work opposite of a conventional O2 sensor. Not only are they more accurate over a wider range, hence the term, the title, but they are also more accurate. They're greater range, greater accuracy. Here's how they work. Now, just want you to look at my hand here, level with the Delphi logo on my shirt. We're gonna call that 14.7 to 1, stoichiometric. And you know if that number goes lower, the 14.7 being the air, 1 pound of, 14.7 pounds of air, to 1 pound of fuel. If it goes lower than 14.7, let's say 12 to 1, 11 to 1, that's a rich mixture, a lot less air for that 1 pound of fuel. But if it goes higher than stoich, higher than my label here, if it goes 16, 17, 18 to 1, that's a leaner mixture. So we need to add more fuel to compensate if it goes lean. Normally an O2 sensor, when you're lean, is going to be a low voltage, high air fuel ratio, higher than 14.7, 16 to 1, for example, low O2 voltage. Think the opposite with these air fuel and wideband sensors, either measuring in a voltage between 2.5 and 3.5 volts or so, or a current, very small current, 20 milliamps typically, of movement. The number of amps, milliamps, positive or negative, will go with the air fuel ratio. So at 14.7 to 1, which by the way is also lambda, the perfect 1 lambda, 14.7 to 1. When you're at 1 lambda, 14.7 to 1, the voltage on some cars and PIDs, you look at the wide type band sensors, will go a little higher from, let's say, 3.3 to 3.6 as the air fuel ratio goes higher, meaning leaner. So it goes right with the air-fuel ratio, as does lambda. 14.7, 1 lambda. Below 14.7, richer, below 1 lambda. Let's say 0.9. You saw the Explorer, when I put the propane in, it went down a few times to 0.9 as that fuel trim made adjustments before it actually had a chance to make adjustments. And when we started going lean, we saw we went stoic, and the current in the case of the Explorer didn't change much, but out in the real world, in the road tests, without the delays, we would see the current go positive and a higher number of millivolts when the ratio went higher, leaner. So air-fuel ratio, 14.7, 16, 12, and lambda, 1, 0.7, 0.9, or 1.1, 1.2, or the voltage of an O2 or the current of the new style O2s go with the air fuel. Hope that little analogy with the hands helps you keep it in really good long-term memory, no pun intended, so when you look at these PIDs, ba-bing, you know what's going on as you drive that car or run it in the shop at idle. All right, first steps in diagnosing air fuel management issues, fuel trim issues. Does the fuel trim variation, let's say it's a negative 30, does that happen only in one driving condition or across all ranges? That's very important to know. Example, you get a vacuum leak and it's a positive number associated, especially with a mass airflow car. It'll be more profoundly positive with mass airflows. So you see, let's say positive 20%, we're adding fuel, but then you go above idle. You get into 1500, 2500, numbers you need to run different ranges as you idle it in the shop, rev it up, and go on road tests and so forth. Watch the trim doing under different conditions. As you rev it up, and that trim goes from a positive 15 or 20, adding fuel because maybe a vacuum leak, that number comes back down again because vacuum leaks don't have the profound effect on air fuel management when you get above idle because a little tiny hole in a gasket or a vacuum hose has fallen off, whatever, is a very small percentage of overall air usage when that throttle is open quite a ways and we're pulling a bunch more air in. Conversely, if you have fuel trim numbers that are normal at idle, but when you get on a road test, they start falling apart and the numbers keep tracking up, or adding fuel, it could be a fuel delivery issue. The fuel pump, it puts out good pressure at idle in the shop. You get out on the highway and the fuel pressure drops, but mainly the fuel volume drops. It can't put out the volume. Therefore, you know when you've got good trim numbers at idle, but positive numbers profoundly as you go up higher into engine load values while you're driving the vehicle, road testing, you probably got a fuel delivery issue. Now, is there a variation between banks? Left bank versus right bank? You got two O2 sensors, one for each bank, and I've got a really low number, negative trim on one side, maybe a drippy injector. I've got a high number on the other side, maybe I've got a vacuum leak on a runner or side of the intake, the plenum or whatever that's leaking. So look at the ratios, kind of compare it to what's going on with the vehicle. You can have a mass airflow sensor problem, by the way, it's a weird deal. And I really can't explain why, but you can have a mass airflow sensor with an issue and affect only one bank's fuel trim. Another thing you want to look at, Mr. Obvious stuff, is the vehicle in closed loop. Now, some vehicles will trim a little bit when you first turn the key on and start the engine. It's programmed into software. So you may see a positive 40% fuel trim. And when you start the engine, it says open loop. That may be normal for that vehicle. It's part of the calibration. Maybe even a long-term fuel trim positive addition will be stored into non-volatile RAM. It'll be actually calculated on the run by the vehicle. If it's a calibrated issue, then you also want to keep in mind on the subject of calibrations, if you replace parts on the vehicle, I got fuel pump was bad, not enough pressure, volume. I had a vacuum leak, I replaced a gasket. You do all those things and you still can't fix the fuel trim issue. Always, always, always check for TSBs, check for updates and other sources of information to see if that manufacturer updated the software in the powertrain control or ECM, engine control module, because you will not replace parts when it's a software issue. So always look to see if there is a sign of an updated software to fix fuel trim problems, because it's not just mechanical conditions, it can be software related. Now, also, first steps in checking for fuel trim issues, check all your DTCs. So if you have a misfire code, definitely fix that first. Fix an O2 sensor problem first. Misfires, for example, will cause the fuel trims to go higher, either be a mass airflow or a speed density vehicle. And here's why. Now, normally a lot of techs will say, well, if it's misfiring, let's say it's an ignition misfire, very popular, very common, doesn't make combustion because there's no spark. Fuel injector, on the other hand, still sprays. Wouldn't it make the mixture rich? Yes, but what does this measure? O2 only. Doesn't measure hydrocarbons. It's not a 5-gas analyzer, it's a 1-gas analyzer, O2. So the oxygen that didn't burn when the fuel sprayed but the spark didn't ignite it goes right onto the exhaust and makes this think it's lean. So fuel trim numbers go up. But here's a little lesser known fact. When you have ignition-related misfires, the fuel trim increase, positive, it will happen, it won't be profound. It won't be 25, 35%. Typically, it might be 10, 12%, 15%. If you have an injector that's not spraying, causing the same lean mixture, the same abundance of oxygen left over, that will have a very profound effect, 20, 25, 30% positive fuel trim. The difference between the two events, they're both lean, they both drove fuel trim. One drove the fuel trim up a little bit, ignition-related misfire. The other one, a bad injector, not spraying fuel, a fuel-related misfire, that one drove the trim up profoundly. What was the difference? The way combustion reacts. So one reacts differently than the other, so you'll just remember O2 increases, I should say trim increases from ignition misfires are less profound than trim increases from a true air-fuel ratio, like a bad injector type of a misfire. So consider those things. Also, late model, speaking of injectors not firing, late model fuel injectors will be shut off if there's an ignition or any other reason for a misfire, and that's only going to affect if you were measuring with a gas analyzer in the tailpipe. So if the PCM is not calibrated in what I would call the right way of doing things, the PCM basically would say, hey, gee, it's lean. I'm seeing abundance of air because it shut its own injector off. So remember, cycle the key, clear the code for the injector before you go back to fuel trim diagnostics. You may just have a misfire issue. Speaking of memories, memory cells and so forth, this XY axis chart here is used for speed density vehicles. You have the Y axis up and down, that's the load, increasing load this way, and RPMs, increasing engine speed that way. On vehicles with map sensor only, we use this type of a table to make little blocks, if you will. It could be 8, it could be 30, whatever. There's some number divisible by 8 typically, or 4. That particular position where that block of memory is will be when we cross the line of so many RPMs and so much engine load, and the computer saw the short-term fuel trim kept maybe hanging low or going higher than 0. We watched it over a course of time and made a correction, a permanent correction or semi-permanent correction in long-term fuel trim, which is stored in memory. So these blocks of memory are what we clear out when we do a fuel trim reset. It's what the computer programs in and keeps in non-volatile memory. In other words, the key cycle doesn't affect it. When it sees a long enough period of time and the PID for fuel trim, long-term fuel trim learn says enabled, that's when these numbers start picking up. Now you see in this chart, the numbers all look within that 0 to 10% positive or negative region. But if you saw positive 30 in block 1, we see in the lower left-hand corner, and all the other numbers tend to be a little bit better the further we went up cross diagonal to the upper right-hand corner, that's more likely to be a vacuum issue, a vacuum leak issue. But if we saw good numbers in the lower left, and as we went up towards our upper right, we saw the numbers go positive in the upper right, meaning higher RPMs, higher load, we're looking for a fuel delivery issue. So looking at these, you don't see this on your scanner, but you could certainly jot a few numbers down. Take a cell phone picture, somebody drives the vehicle for you. Don't operate your cell phone and a scan tool, for crying out loud, while you're driving for safety's sake. But as you record these things under these different load and RPM conditions, you have a really spot-on chance of defining what's causing the trim to do what it's doing, so you can diagnose the problem right the first time. If it's a speed density car, it's going to have that dimensional chart that we just looked at. If it's mass airflow, it's just blocks in a row for, let's say, 20 grams per second, 50 grams per second. It's just blocks in a linear fashion, but it's the same process of memorizing these different conditions that occurred 2 minutes ago or 2 days ago. It's all kept in memory. Now, those memory blocks are not created equal. We see some numbers, and these are in the old block learn integrator format of numbers, like 160 and 165 and so forth, 175. But you can just say those are positive numbers. We're adding fuel. These different blocks of memory have different values of importance. The engineers have said, you know what, in block number 5, that is a 67% weighted value. That means that's 67% of importance. And you see those lesser numbers, 22%, 11%, those are still blocks of memory, and we'll still consider them as we change the air-fuel ratio a little bit to adjust for O2 variations and problems, but not as much as block 5. So keep that in mind as well, that they're not all created equal. They're going to vary from car to car where they put the weight or importance of the fuel trim memory. Let's do a little on-car demo now of a vehicle that has a mass airflow and conventional O2 switching style sensors. Mid-2000s Lincoln here with the mass airflow sensor. We're going to do some classic mass airflow equipped vehicle fuel trim testing here. A couple problems bugged. One of them is going to be lean. We're going to see that first. The other one's going to be rich. Let's go ahead and start it up, and let's watch our scan tool PIDs. I've refined them down from my O2 customized list. I want to look at RPMs just to see what she's doing. I'm going to see, make sure she goes into closed loop, and I have no O2 sensor faults. We won't run a fuel trim monitor unless we've got good O2 sensors. So no faults, status okay, front and rear O2s, pre and post catalytic converter. We've got -3% fuel trim, both banks, positive 36% long-term fuel trim, both banks. So the long term has not responded yet. We first started up, we are closed loop. I would anticipate with that much additional fuel being applied in this very lean mixture, as we see the O2 sensor, bank 1, sensor 1, 0 volts. So that is really low voltage. We are really lean. We're adding fuel. Now, when you make an adjustment, when you unplug something, when you replace a part, you always want to, if there is a learned fuel trim, you want to, long-term fuel trim in memory, you want to clear that and see what happens, if that actually changes anything. That gives you a good clue. I go back to no additional or no subtractive, no multiplicative or subtractive, additive I should say, or subtractive pulse width modification. If I go back to 0 and I have it run better or worse, that's a good clue of what's going on here. We are certainly lean. We're adding 34% on the short term. Let's go ahead and see what we would do in a case like this. Now, looking at the parts on the table, what could cause low O2 output? What could cause a high fuel trim number? Well, anything to make it be lean. So we look for vacuum leaks, false air, not just vacuum, air that the mass airflow sensor does not get to read, so the computer doesn't know it and doesn't add the fuel to go with that air, so we're lean. We could smoke it with a smoke machine, look for smoke or signs of dye with the ultraviolet light and the glasses. We definitely would want to measure fuel pressure. Too low a fuel pressure would make it run lean and make the fuel trim numbers positive. We could also look to see if we had alcohol in the gas. It would make it lean. We could see if we have a restriction. If we have a fuel pump, fuel pressure number lower than specs, look at the restriction. Maybe a good old-fashioned filter or the sock on the bottom of the pump even could be restrained. It could be a damaged pump, something wrong with the turbine or whatever, not making enough pressure. In the type of pumps that have the bucket, the modular assemblies, there's something called a jet pump. Nothing to do with the electric side of the system, electric pump. There's an electric pump there, but on the bottom of that modular assembly, a little jet, the fuel goes through like a valve. Fuel pressure regulator in the modular assembly on the returnless systems, or if this is an old style that has the return system, the vacuum operated fuel pressure regulators on the rail. Anything that could cause the fuel pressure to be low could cause what we're seeing right here. A fuel pump that's not getting enough voltage due to a resistance somewhere in a connector, even resistance across the contacts in the relay. We got to make sure we do a good voltage drop test at the fuel pump to see if the fuel pump's got proper voltage. If we see low pressure, that's accompanied by our root cause here, and that is very high fuel trim numbers, very low O2 voltage. And finally, looking at sensors. Is the coolant sensor, if it's shorted or open, we'll get a code for that. But if it's skewed, if the internal thermistor in the coolant sensor or intake air tip sensor is a little bit off, and if it's saying it's hotter than it really is, it will not spray as much fuel as it should during the base pulse width spray. The O2 sensor will respond by saying it's not got enough fuel. I got way too much O2 left over, and the positive fuel trim numbers will be the result. So any of these things, and one more thing, restricted injectors. Not enough fuel being sprayed at the engine. So those are all part of what call the usual suspects on a lean mixture. Now let's do the reverse of this and look at a rich mixture on the same car. Same mid-2000s Lincoln Continental with a rich mixture now. We got a mass airflow sensor also. Now we have negative numbers on the short term. Long term will eventually come up to meet. There'll be different cells as we drive the vehicle. It's essential to look at the cells as we drive the vehicle to see which cells of drivability, high RPM, high load, or lower RPM, lower load, are good information sources for you to determine, do we have vacuum leaks, do we have fuel pressure issues, fuel delivery issues. In this case, because we are showing negative fuel trim numbers as indicating that the O2 is higher than normal. As you see, it's kind of hanging out mostly in the higher numbers, 0.7, 0.8, and so forth, occasionally going lean, trying to make the switch, trying to do fuel control, but negative 16 to 18 on the short term, that's definitely indicating a rich mixture. So what will we do there? Well, we don't really need to use a smoke machine because the rich mixture is going to be too much fuel pressure. So that's one of the first things we'll look at. It could be a fuel pressure regulator, either in the tank, if it's a modular assembly with a returnless system, or the older systems that had the return system in the rail with the pressure regulator on the rail. That would cause it to be overly rich. We could have drippy injectors, so we want to make sure we look at the pressure and do an injector pressure drop test. Also, there are tricks you can do with your gas analyzer to see if the injector is what's dripping, and on an oscilloscope as well. A skewed O2, a bad O2 sensor could cause rich or lean. It could be sensing falsely. Other sensors, the coolant sensor, intake air, could be saying it's much colder than it is without being a complete dead space of low voltage or extremely high voltage, what we call the dead zones, setting the code. It could just be skewed. So those could all cause a rich mixture that could result in what we're seeing here, some negative fuel trim numbers. Now what we want to do is to pull a vacuum leak and see if the O2 sensors respond. If they respond and the trims seem to straighten out, we truly did have a rich mixture. So you do the opposite. You use the propane. If you see lean, fatten it up, see if the O2 sensors respond, then you know it's really lean and it's not an O2 sensor that's unresponsive. So sometimes it's hard to determine which comes first, the chicken or the egg. Is it an O2 not responsive and we have trim numbers trying to compensate because we're not doing a good job of air fuel management, or is it an air fuel management issue to start with and the O2s are properly reporting that information? So if you see lean, you make it go rich with a propane or some other source to make her go rich. If you see it rich, in this case we are rich, so we're taking fuel away, negative fuel trim numbers, we'll pull a vacuum leak, do some false air, and see if we can make it go the other way. Let's go ahead and do that now. Pull a little vacuum leak right here at the brake booster and see if those negative trim numbers, short term, and if that O2, which is kind of hanging out quite a bit in the positive, in the rich area, above 0.6. So now I've got some lean going on to compensate for the rich, and we are compensating. O2 goes to the basement, goes to 0, very low, not switching much because it's very lean, big vacuum leak. With a mass airflow, we can do this. Speed density just speeds the engine up because it says, hey, we have less vacuum, I'll add more fuel. In this case, this is air the mass airflow doesn't know about. So mass airflow sensors, you see the low trim numbers, negative, pull a vacuum leak. If the numbers come up, and they really did, and the O2 goes down, then you've probably got a decent O2 sensor to work with. Now it's time to go looking for why it was rich. And one thing we can do, if we think we have mass airflow, we want to do testing there, but if we think we have an issue with a plugged air filter, we simply can lift up the air filter here and see if these numbers change now. So now with the air filter out of the system, I'm just sucking some fresh air from the shop here. I'm no longer having the negative numbers taking fuel away. A little bit negative, but not too bad. I think we just discovered we have an airflow restriction causing this Lincoln to run rich and fuel trim numbers to go low. Negative O2 to run higher. Now we're looking better. We're in better control. We need to look at this air filter. Well, let's go take a look and see if maybe we have a lack of air due to a restricted air filter causing this mixture base pulse to be modified by the negative fuel trim numbers. We're running rich, so we're compensating by a negative fuel trim number, meaning we're taking fuel trim, taking pulse width out of the equation. Let's look at this air filter. I wonder if they've changed it lately. Oh my gosh, look what we got here. We may have pay dirt, no pun intended. Pay dirt, sorry. Hey, other things that can cause a 171 and 174 before we get to what can also cause rich conditions is you can have a faulty mass airflow. Now, speaking of mass airflows that are faulty, is it really the engine breathing less or more, or is it the mass airflow lying? Which comes first, chicken or the egg? Go visit the Delphi Auto Parts YouTube channel, where we're on right now, and look up the mass airflow program. There's also a great program on, we'll talk about later, on the alcohol testing, which can affect drastically your fuel trim numbers. So check out how to test mass airflow sensors using the volumetric efficiency test. We have that on our YouTube site. Check that out. Now, faulty mass airflows, how do they work to go bad? To make it lean, set the lean codes. Well, if you get a piece of contamination on the hot wire, it can insulate the hot wire so it doesn't see the amount of air truly going to the engine, doesn't spray the right amount of fuel then, sprays less than it should, and therefore you're lean. Exhaust leaks, obviously, as you well know, probably, are going to dilute the exhaust around the sensor with some fresh air. Not only do we get positive pressure pulses out the hole where the exhaust leak is, but the negative pulses between exhaust strokes can pull in oxygen and dilute the O2, thinking it's leaner than it really is, and therefore the trim numbers go high and eventually set to code. PCV valves are designed to pull crankcase vapors from the crankcase in the engine and burn them for emissions reasons, but they can also be miscalibrated, because they are truly, technically, a calibrated vacuum leak. So the wrong PCV valve, improperly calibrated PCV valve, can also cause the lean codes for fuel trim. Rich codes for fuel trim. What else can cause those besides what we talked about with the hands-on demonstration? A faulty mass airflow, again, this time contaminants on the intake air element of the sensor can make it think that it's actually a little bit colder than it really is, so we spray more fuel. PCV valve, this time being plugged up, not being the proper calibrated vacuum leak it's supposed to be. EGR valve stuck open, or the exhaust camshaft in a position for variable cam timing that does internal EGR, doing the same job of EGR, staying advanced, sorry, retarded I should say, so we have EGR when we shouldn't have EGR. So that's going to dilute our fresh air and make it richer, and that's going to cause 172, 175 code. Diluted engine oil. Anytime you're going to have a PCV system pulling crankcase vapors, if those crankcase vapors of oil also have a bunch of gasoline from the drippy injector or some other issue, got gas in the crankcase, you'll have the rich codes. Vacuum controlled pressure regulator. We talked about the pressure regulator, maybe the wrong pressure, but it also can just be the rupture. And anybody who's worked on cars for more than a week, I think, has seen this, where you have the good old-fashioned fuel rail with the return line and the vacuum operated pressure regulator and the little vacuum hose. You pull it off, you take the hose, you tap it in your palm, some fuel falls out, bing, that is a rich mixture, and that's a code 172, 175 waiting to happen. Those are just as common as can be. Now, as we look at some things less common, if you are a high-end technician and you use a lab scope, either primary or secondary side of the ignition coil, it's the same pattern, just different voltage levels, and you see a great looking pattern for one of the cylinders. It looks like it is third from the right here in this capture. And that looks great, but the others look like, man, we're getting really lean on that burn line, and it starts having the turbulence and going up and up and up because we're running out of fuel to burn. Though all the other cylinders look like heck, that one is the only one that looks good. That would not be, the one that looks good is actually not the good cylinder. It's the cylinder with the drippy injector. Most systems, unless it's a very new car with what's called fuel trim imbalance, cylinder to cylinder imbalance, if you don't have that, and we look at the fuel trim as a whole on either the whole engine or one bank, the O2 sensor is going, boy, this is really rich on this bank. And so the trims keep going down and down and down, negative, 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 until all the cylinders that weren't dripping, didn't have the drippy injector, all but one, now run out of fuel, have maybe intermittent misfires and some really nasty looking ignition patterns. The one that looked good was good because the drippy injector was being leaned out so much with the base pulse width that dripping and a little bit of spray was just the right amount to give it a good pattern. So keep that little nuance in mind as you look at your patterns if you're doing fuel trim and you've got a scope you're used to putting on ignition and looking there. That's a view inside the combustion chamber using that scope. Now let's take a look at fuel with alcohol in it, and we'll wind out for today's program. You have this PID here on a GM flex fuel vehicle. It says 8% alcohol content because its alcohol composition sensor is at 58 hertz. When you see something like that in a flex fuel vehicle, that's A-OK. Let's watch a little clip on how to determine what your customer's vehicle's fuel composition is with some simple hands-on tips. Fuel volatility, fuel contamination, and alcohol content have always been moving targets for drivability for both cold start and fuel trim issues from the very beginning, from carburetor days up till now with gas direct injection, sequential, you name it. So some of the tools from yesteryear, like this read vapor pressure test kit, where you literally take a cup of water and you put this coffee cup in the microwave, you heat it till it boils, and then you get a sample of gasoline from an approved container, put it in this little receptacle right here, and when this thing goes in to the little hot water, you watch for the temperature to come back to 100 degrees Fahrenheit. And at 100 Fahrenheit, whatever that pressure is, that's called the read vapor pressure. In the winter, it's got to be higher for the fuel to be more volatile, to vaporize and burn easier for cold starts. But if it's too high, like winter gas in the summer, it can cause vapor lock and drivability issues. So this is not as big of a problem as it's been in the past, but what is a big problem now with not only E10, but E85, the flex fuel in vehicles that aren't flex fuel, like right behind me, a Ford, late model Ford, that would have a traditional yellow gas cap, or with the case of the capless vehicles, we would have yellow writing on the filler neck that says E85. This one says E10 to E15. E15 is not really out there too much yet, but E10 is about every gas pump you get. But if somebody gets some E85, maybe half a tank, and they have the other half of the tank that was already in the vehicle that's E10, then you have drivability issues, very severe, and fuel trim numbers will go positive because the alcohol content in the tank is not got enough energy, and the computer doesn't know you have alcohol, so it doesn't adjust the base pulse width like a flex fuel vehicle would with a virtual sensor, which is using fuel trim after a refuel, or an actual alcohol test sensor, a sensor that measures the alcohol content going from the tank up to the engine. If you don't have a flex fuel vehicle, there is no way it knows. It just knows this something's really lean. I don't have enough fuel. It sprays more fuel to compensate and sets the lean codes, 171 and 174. So what we got to do is check a good sample of gas from the tank. So I pulled some gas out of this particular non-flex fuel vehicle, and I put it into a little test tube. Now what I'll do is I will first pour 1 ml of water into the bottom of the test tube, and then I will fill it up to 10, so 9 mLs of gasoline from the vehicle and 1 ml of just plain old tap water. And you shake it up real good and let it set for a few minutes. The separation line, if you have pure gasoline, no alcohol whatsoever, will be at the 1 ml. It'll be the very bottom right here. because gasoline is lighter than water. The water will sink to the bottom, whether it be in the gas tank or in this little test tube. So as we let it settle, we see this one over here on your right is at 1, actually it's a little above that because it's E10. E10 is normal pump gas. So that will mix some of that water into the overall sample because water is sustained or suspended in alcohol and the alcohol mixes with the gas. So I've raised from 1 ml, which is what the water I put in here, up to almost 2, about 1.7. So we have about E7, about 7% alcohol in the gasoline, quite acceptable for this Ford that's not flex fuel. On your left here, I have a sample that, again, I put 1 ml of water and 9 mLs of fuel from another test vehicle, but it came in on a wrecker. It wouldn't start. It had drivability issues and it had lean codes. So we did a sample, 1 ml of water, so the separation line should be maybe between 1 and 2. If it was at 2, that would raise it up 1 notch, which would be 10% or E10. But look where the separation line here, over here was it about 17 or 20, between 17 and 20. Here it's almost up to about 55 or 60. So this is about E50 or 60. This is a very high alcohol content with the separation line clear up here, indicating we have an issue. If it doesn't say flex fuel on the filler neck, doesn't have a yellow cap like this that says E85, then if you have a sample like this drawn from your customer's vehicle, you have your answer to why fuel trims are raising positive numbers, compensating for a very energy poor gasoline and also giving you drivability problems. One last point I want to make, and then we're going to open up to questions from you guys in the field, is the side of the mechanical nature of the engine. Now, if the engine has any aftermarket components, it's got bigger throttle body, it's got a different camshaft and a different intake, it's going to affect volumetric efficiency and it's going to affect fuel trim unless it's had a calibration update to go with the performance parts that have been put in the engine. But if it's just got normal stock parts in the engine and there's a problem, you've got overheated cooling system, a head gasket issue, a valve that won't seat, those kind of things, since most of us don't have a 5-gas analyzer. If you did, you could take a chart like this and nail exactly, by looking at all the gases of the 5 gases, you come up with the solution of what's probably causing the problem mechanically if it's not an air, fuel, or ignition issue. But in the case of our O2 sensors, we do have one of those machines in the shop. It's called the O2 sensor in the car. We've established it's working, it's responsive. Now we look and say, okay, all these conditions in highlight here under O2, which is what we can measure without a gas analyzer, just with a scan tool. All of them say high O2. That's going to mean a low fuel trim number because the O2 went high. That's going to result when we have all these different conditions from carbon, low compression, exhaust valve burnt and so forth, pre-ignition. All that happens, you got O2 that's high. When the O2 goes low, it's because of low compression or camshaft timing, either early or late. So we have variable camshaft timing with maybe a cam phaser issue, or if it's not a variable cam timed vehicle, it's just got a solid chain or belt, maybe somebody put the cam in wrong. So those kind of things enter into it as well, so don't overlook the mechanical things when you do your total fuel trim diagnosis. Now let's open it up to you folks in the field. What questions do we have, Steve? We have any already?
Okay, Dave, our first question is from Pete, and he asks, what is the difference between the P.I.D, short-term fuel trim bank 1, and short-term fuel trim bank 1 sensor 1? They are often used on the same vehicle, and do you add all 3 together to get total fuel trim?
Wow, Pete, that's a great question, and I wish I had an absolute definitive answer. My gut tells me that they're basically the same P.I.D. If you know how non-factory scan tools work, whether it be brand X or brand Y, if it's not the factory tool, the manufacturer of the scan tool, buy the packets of data from the various OEMs. And with the packets of data, they'll have some errors that were because of early production changes until the final production goes out on that vehicle. And the manufacturer of that scan tool has to tweak and find out what those errors were. And sometimes it's a matter of trial and error. Oftentimes you will have more PIDs on your factory level or OE level aftermarket tool than there are applicable to the vehicle. If you had the true factory tool, you would just have the PIDs that are germane. They're actually valid. I've actually seen on some aftermarket OE level tools a diesel injector PID or a glow plug PID for a gas engine. So you know something was really cooking with that, right? So those things happen, and my gut says that's probably what's going on, especially, Pete, if you've seen the same number for both short-term fuel trim bank 1 and short-term fuel trim bank 1 sensor 1. If they're the same number, it's the same PID. Now, if it's not the same number, we may be looking at something like a second O2 sensor, a second catalytic converter, first and second cat, and so forth. So some pretty crazy stuff they do with newer vehicles, adding a pre and a pup converter and a secondary converter and O2 on each side. Those kind of things, we may be seeing multiple O2 sensors, so they are defining them in a little bit of a funky way. I'm not sure there, but go ahead and look. Next time you see that, Pete, if those two PIDs have the same value, it's the same thing.
Here's a question. What is a PID?
I'm glad somebody asked that question. PIDs, TIDs, SIDs, MIDs, that's an acronym. And boy, we are just alphabet soup with acronyms in this business, aren't we? PID stands for Parameter ID. It's short for data PID. You know what data is? That's RPMs, mass airflow, map, coolant, temp sensor, so forth. So a PID is basically what you see on your scan tool for live data. And so if I refer to fuel trim PID or mass airflow PID, I'm just saying like the mass airflow value or the fuel trim number that's on your scan tool. But I get that question asked quite a bit. I guess I'm guilty of just using too many acronyms myself. So I get it honestly. I hang with engineers here at Delphi, so we love acronyms, both in the automotive engineering world and I guess the military may be the #1 in the world using acronyms.
Here's a question from Dawson, Dave. What effect do gasoline additives have on fuel trim?
Dawson, they have a lot of effect on fuel trim. I want you to think about the little hands-on demo we did with the alcohol content. If you ever see what's inside, if you look at the ingredients of, let's say, fuel line antifreeze, if you live up north, then that's a problem. Fuel injector cleaner, the main component is isopropyl alcohol. Alcohol, whether it be methanol, ethanol, it's alcohol. And it's going to dilute out the gasoline to a lesser power, lesser BTUs, and that's going to make a leaner mixture, and that's going to make the trims go higher. It's also too much of a dilution, too much dosage of an aftermarket additive to a fuel system can cause fuel system damage, not only to the fuel pump, but to filters, elastomers, let's say the O-rings around the injectors, you name it, even the tank's plating if it's an older vehicle with a metal tank. So make sure your customers know, follow the directions on that additive, and certainly if they're going to err on the side of conservatism. Less cleaners, less additives, the better. Don't go overboard. It's like taking too much medicine. It can actually be worse than not taking your medicine at all.
Oh, we got one here for you, Dave. How can you determine a bad air fuel sensor affecting fuel trim?
Thanks for that question, Steve. Air fuel sensors are pretty reliable, #1. #2, when they go bad, they usually code. There's usually a DTC specific to an air fuel sensor problem. Now, one thing I will mention about them, I don't have the rest of the sensor. I just wanted to show you the connection right here. This is the connection to the harness. This is the connection, of course, I clipped off of the actual sensor. You'll see a little circuit board, it looks like right here. And what's in the middle of that circuit board is a little carbon resistor material that's etched or burnt with a laser, trimmed to just the right resistance value. These things are very complex, very fussy. You never back probe on this side of it because you could break that little board and cause that resistor to make this thing go out of kilter. When it does, it should set the code. But a lot of technicians are looking into, the high-end guys and gals, looking into buying micro ammeters. So we got ammeters that can measure milliamps, but this is too low of milliamps for the typical amp clamp, and nobody wants to break a connection out, a terminal out, and put an ammeter in series. So to use an inductive amp clamp, they're looking into micro amp clamps. They're pretty pricey. I mean, they're hundreds of dollars, but a lot of techs are having some luck using the micro amp clamp to go around inductively around a wideband or air fuel sensor, and then hooking that into their lab scope and seeing those 5, 10, 3, 4 positive and negative current patterns, and making decisions like we did early on 30 years ago with the switching style O2 sensors, watching those with scan tool graphing and scopes. So I anticipate maybe in the future we may do a wideband and switching O2 sensor program, but for now that's a little high-end overview of these sensors. They should code. Obviously the propane, the vacuum leaks will have some success, as you saw on the Explorer. Limited success on making that wideband sensor get excited one way or the other, but it does happen. So that's one other thing you can do is just good old-fashioned drive them rich and drive them lean and see if the trims change, see if that sensor's changing its value. Obviously you can look at the post-cat sensor as well.
Okay, Dave, we're really out of time, but we're going to squeeze in one more question here from Mike. And Mike logged in late, so you may have covered this, but he wants to know, what's the relationship between lambda and fuel trim?
Very good. Great question, Mike. Thanks for asking that. And I don't know if you logged in about the time before or after. I was using my hands here. But stoichiometric, right here, level with the Delphi logo, 14.7. You go lower than 14.7, you're going richer, 12 to 1. Less air to the same amount of fuel. Fuel trim is going to go the opposite direction. So lambda and air fuel ratio are essentially the same. One lambda is 14.7 to 1. 1.1 or 1.2 lambda, higher than 1, is a higher air fuel ratio, 16 to 1, 15 to 1, higher than stoic. Less than stoic, 12 to 1, is less than 1 lambda. It's 0.7, 0.8, 0.9 lambda. So when you see the mixture go lower than 1 lambda, lower than 14.7, that's rich. You know what fuel trim does. It compensates by taking fuel away. Negative fuel trim numbers. As you see lambda and air fuel ratio, 14.7, 1 lambda, go higher than stoic or 1 lambda, 1.2 lambda, 16 to 1. Then we're lean, and you know what fuel trim does. Actually adds fuel then, positive fuel trim numbers. So that's the relationship. Mike, thanks for asking the question because I think it's a concept that's new enough to a lot of us older techs especially that we really need to have it said a couple of times to get in the long-term memory. So when you hook that scanner, you go for that road test, it's second nature to you.
Well, thank you all for joining this live stream event from Delphi's training series powered by AVI. If you missed any of the previous broadcasts, they can be found on Delphi Auto Parts YouTube channel. And be sure to follow Delphi Auto Parts on Facebook and Twitter for regular updates from Delphi. And don't forget to stay tuned for future live stream training events. On behalf of Delphi and AVI, thanks for watching.